Now, rewinding the mechanism of dehydration of alcohols. In presence of concentrated sulfuric acid, the main species is H positive, not H3O positive, because concentrated sulfuric acid contains little amount of water, and this water is in the protonated form, and there is very small amount of water, and hence there is a large excess of H positive, and hence the mechanism starts with the H positive. Even if it is H3O positive, there is no harm. Now, protonation of alcohol using lone pair of oxygen, we get the corresponding protonated alcohol. It's a fast reaction because the lone pair can easily be donated to H positive in acid medium, and again it's a reversible reaction because the H positive may be removed from this ion to get back the original alcohol easily. Now both forward and backward reaction occur, and there is an equilibrium between the free alcohol and then the protonated alcohol. So it's a reversible reaction. Now H bond may be easily broken from this OH2 positive parts. Now then second step is the removal of OH2 positive as a molecule of water. Now a carbocation is formed. Now this can be attacked by this nucleophile water to get back the protonated alcohol, so that this reaction is reversible. So carbocation being attacked by water as a nucleophile, and I said a primary carbocation, primary alkyl carbocation, that should be specified, because there are other primary carbocations which are stabilized by resonance, etc. But this alkyl carbocation, which is primary, is least stable, and it may be formed in this reaction, and it may be due to the high temperature used and the strength of the acid, which is highly polar. That may be the reason why this is stable in this medium. Now this is attacked by base in the beta position. This is alpha and this is beta. So a beta hydrogen, that is hydrogen connected to beta carbon, is being attacked by HSO4 negative as acting as the base, and removal of this H as H positive, shift of this bond in this direction between alpha and beta positions, we get the alkene and H2SO4. Now here this alkene can be attacked by H positive because sulfuric acid is mostly in the ionized form, H positive, HSO4 negative. So this H positive may be attacked, may attack this alkene, liberating this carbocation. So this reaction is also reversible, and what is done is this ethylene gas is driven out from the medium by heating, and so that overall equilibrium is shifted towards the right. Now that is the mechanism in brief. Now coming to one conversion reaction, that is conversion of a higher homologue to a lower homologue, RCS2CH2OH to RCS2OH, and here RCS2CH2OH is the higher homologue and RCS2OH is the lower homologue. These two differ by a CH2 group. Now one CH2 group is reduced from this structure, and this is called descending the series, descending and ascending. Ascending is the opposite of descending, so you have to descend this series, this compound, to its lower homologue. Now what is done is, you have seen that concentrated sulfuric acid, phosphoric acid, then anhydrogen chloride and alumina, that is Al2O3, can act as dehydrating agents. Now here for the conversion we use alumina Al2O3 at 350 degrees Celsius, so that From the alpha carbon OH and from the beta carbon H are removed. Now in the case of a primary alcohol, it's a primary alcohol. There is only one beta position, so the one ene is formed easily. Now what is done is this compound is subjected to ozonolysis. Now ozonolysis means addition of ozone followed by hydrolysis. Now that reaction may be represented like this: C double bond C reacting with the ozone, and here ozone splits into oxygen and O2. Now oxygen is divalent, so it has two valencies. Now O2 is O double bond O. One pi bond here may break to create two valencies over oxygen atom. Now when ozone reacts with an alkane, what happens is that one pi bond here breaks, creating two valencies over these two carbons. Now this oxygen atom with its divalency will unite with the valency here and the valency here. So we get C bond O, C, then so this oxygen atom unites with these two carbons by breaking of this pi bond. Now this bond will break, creating two valencies like this. So there are additional two valencies over these carbons. They are shown here. Now this bond breaks and creates two valencies. Now this O double bond O breaks one pi bond and creates two valencies. These two valencies unite with these two valencies to form two bonds. So we have O bond O here. Now this cyclic structure, ring structure, is called ozonide. Now ozonide can react with the water, and here water reacts in this manner. You put a vial like this, and these lines show bond breakages. This here bond is getting broken, this here bond is getting broken, this O bond is getting broken. Now water combines with this O, H2O plus O giving H2O2. Now these two valencies unite, this valency and this valency unite to give C double bond O, and this valency and this valency unite to give C double bond O and H2O2. So these are the products. Now here zinc and dilute acid is used because this hydrogen peroxide is an oxidizing agent. If this is an aldehyde, means if you have one H here, then this hydrogen peroxide will easily oxidize this aldehyde acid. So what is done is this hydrogen peroxide is destroyed by using zinc and acid. So nascent hydrogen will be produced here by reaction between zinc and acid, and that nascent hydrogen will reduce the oxygen produced by decomposition of H2O2. H2O2 can give H2O and O, and this O will be reduced by hydrogen produced from zinc and dilute acid giving water. So H2O2 is destroyed by this reagent system, zinc and dilute acid. The net reaction is here. The double bond breaks completely and one oxygen is connected to each valencies. So double bond breaks completely, two valencies are created. Since oxygen is divalent, that is connected to these valencies, This oxygen is divalent connected to this valency, so that the net reaction is formation of C double bond O plus C double bond O, and this complete process is called ozonolysis. So this alkene on ozonolysis, we can say that the double bond gets broken, two valencies united to one oxygen atom. The valencies here united to one oxygen atom. We get RCHO plus the next compound is CH2 double bond O. So we need not consider this compound. We consider only RCHO. Let it be formed. Then this RCHO can be reduced using hydrogen and palladium to CS2OH, RCH2OH. So it's a reduction reaction where CHO is getting reduced, RCH double bond O plus HH. This bond breaks, two valencies are created, one valency connected to hydrogen. This bond breaks, one valency connected to hydrogen. So this becomes RCH2OH. So reduction of aldehyde using hydrogen and palladium, or you can use lithium aluminum hydride, or again you can use sodium borohydride to produce the corresponding alcohol RCH2OH, and this is the higher homologue of RCH2OH, or RCH2OH is the lower homologue of RCH2CH2OH. So this is called descending this alcohol series, descending, decreasing the carbon number. So when you are asked how will you convert this higher homologue into lower homologue, first of all treat it with the alumina, then that reaction is dehydration reaction, removal of water molecule, you get alkene. One alkene is always formed from a primary alcohol. Then second step is ozonolysis. It is simply breakage of the complete double bond. Then to the two valencies you unite one oxygen, because oxygen is divalent. To these two valencies you unite one oxygen, which oxygen is divalent, and we get two aldehydes here, RCHO, and there is important formaldehyde, CS2 double bond O. You take RCHO and reduce it using hydrogen and palladium, or better lithium aluminum hydride, or again sodium borohydride may be used to get RCH2OH. So that is a useful conversion reaction. And here for dehydration, alumina at 350 degrees Celsius is used. So it's a good conversion reaction, maybe asked for exams. Now you write down these steps. Now, oxidation of alcohols. The two main oxidizing agents used in chemistry generally are acidified potassium permanganate, that is KMnO4 containing dilute acid, dilute sulfuric acid may be used. Dilute hydrochloric acid is not used because KMnO4 oxidizes dilute hydrochloric acid to chloride, so dilute sulfuric acid is used. Then acidified potassium dichromate, K2Cr2O7, that is K2Cr2O7 containing dilute sulfuric acid, of course. There again we cannot use HCl because a compound called chromyl chloride is formed. That complicates the situation. So they oxidize a primary alcohol to an aldehyde, RCH2O to RCHO, but an aldehyde is very easily oxidized by oxidizing agents. That is one difficulty. So as soon as RCH is formed, it is soon oxidized to immediately oxidized to RCOH, the acid finally. So a primary alcohol, first stage is oxidation to aldehyde and next is easy oxidation to acid. Now a secondary alcohol using these reagents can be oxidized to a ketone first. So you take CH3CHOH, CS2CH2CH3 oxidized to CO. That means 2 H atoms are removed as a molecule of water. So we get C double bond or structure, that's a ketone. Now a ketone, on further oxidation with these reagents, we get a mixture of acids. Now here the CO group will be in company with the smallest alkyl group, so that this bond breaks and CH3COOH is produced, and this portion is oxidized to CH3CH2COOH. This carbon is oxidized to COOH. So this carbon is oxidized to COH. This CH2 group is oxidized to COH, and CO groups keeps company with the smallest alkyl group, that is methyl. Here we have propyl and methyl alkyl groups, and CO groups keeps company with methyl, so that we get CH3COOH. So a mixture of acids are produced, each acid containing a lesser number of carbon atoms than the parent compound. Here the parent compound contains 5 carbon atoms, but this acid contains only 3 and this acid contains only 2. So each acid contains a lesser number of carbon atoms than the parent compound. Then if you want, you may write these points. Now, since strong oxidizing agents oxidize the aldehyde to the acid or the ketone to mixture of acids, oxidation using strong oxidizing agents is avoided for the preparation of aldehydes and ketones. Now, mild oxidizing agents like chromium trioxide can oxidize a primary alcohol to an aldehyde. We can stop the oxidation at the aldehyde stage, and again a secondary alcohol to a ketone. So further oxidation is prevented using a mild oxidizing agent like chromium trioxide, so that RCH2OH, 2 H atoms are removed from these two atoms, one H from OH, the other H from CH2. Oxidizing agent supplies nascent oxygen, so these 2 H atoms combine producing water, and this group is converted to CHO. Now the simple mechanism for oxidation using chromium trioxide. Now here the lone pair of oxygen atom is donated to chromium. To maintain the valency of chromium, this CRO bond ionizes towards oxygen, so we get O negative, and when this lone pair comes into a bond with chromium, chromium should get a negative charge, but when this bond ionizes, chromium gets a positive charge, and the negative and positive charge neutralizes, so there is no charge, and the charge is over oxygen atom, it becomes negative. We get a bond between O and Cr, oxygen gets a positive charge, and this OH bond shifts over oxygen atom, means the electron pair in the OH bond is taken up completely by oxygen, so that H is removed as H positive, and the charge over oxygen atom is neutralized. and H positive comes in contact with O negative producing OH. So we get such a complex compound. Now in the second stage of the reaction, the alpha CH bond shifts in between this C and O. So this bond is rotated through, say, an angle of 90 degrees and comes in between this oxygen and carbon. To maintain the valency of oxygen, this bond is shifting our chromium, and that will give negative charge to chromium, so that this bond will be shifting our oxygen, means this pair of electrons will be taken up completely by this oxygen. So we get O negative, and when this bond shifts in this direction, H positive. H positive combines with O negative to form another OH, and there is double bond O. So we get RCHO and Cr OH twice, double bond O. H2 CrO3, and this is sometimes called chromous acid. So that is the mechanism. If you want, you may write the mechanism. Now a better reagent used for oxidation of primary alcohols to aldehydes is pyridinium chlorochromate. Pyridinium, Pyridinium chlorochromate, abbreviated as PCC. One advantage of this reagent is that it will not affect a carbon-carbon double or a triple bond. It will affect only the primary alcoholic group CH2OH. So pyridinium chlorochromate is obtained by the reaction between pyridine HCl and chromium trioxide. Now pyridine, we have seen earlier, is an aromatic compound, and then the nitrogen atom in pyridine contain a lone pair, so it is a base. Now base can react with HCl, that is acid. The lone pair of nitrogen is given to H positive, we get NH bond, and the positive charge is transferred to nitrogen, and this ion is pyridinium ion. Then this chloride ion will give company with this positive ion. So pyridinium chloride, in presence of chromium trioxide, chloride ion attacks the chromium to a lone pair of chlorine is given to chromium. Then the valency of chromium increases and it gets a negative charge. To maintain the valency and to neutralize the negative charge, the chromium to oxygen bond will be shifting like this over the oxygen. And we get O negative and a Cl bond. Now this pyridinium ion with a positive charge, and this chlorochromate ion with a negative charge, combinedly called pyridinium chlorochromate. Now a primary alcohol attacking this chlorochromate ion. Then the lone pair of oxygen is given to chromium. To maintain the valency, the CO bond will be shifting like this. Then to neutralize the charge of oxygen, this OH bond will be shifting over oxygen. We get H positive, that is getting connected to oxygen. We get OH group here, double bond O negative and Cl all are present. Now in the second stage, as in the case of oxidation of primary alcohol using chromium trioxide alone, a CH bond in the alpha position, a CH bond connected to alpha carbon, the CH bond will be shifting like this, simultaneous shift of electron pair like this to maintain the valency of oxygen, and chromium gets negative charge. To neutralize the charge, this bond will be shifting over oxygen, means oxygen gets a negative charge, and this H as H positive will combine with O negative, producing OH and this ion. Then if double bond is present, PCC will not affect this double bond, it will oxidize only this CH2OH to aldehyde, not to acid. Now the use of pyridinium chlorochromate in preventing the oxidation of aldehyde is that the acid produced in the reaction, previous reactions are neutralized by this base. So any acid produced is neutralized by this base, and hence the use of pyridinium chlorochromate prevents the inclusion of acid into the system, and if there is acid, then acid can liberate nascent oxygen from the oxidizing agents like K2Cr2O7 and KMnO4. Only acidified KMnO4 and acidified potassium dichromate or again alkaline KMnO4 can function as an oxidizing agent. So acid is avoided in the reaction with the pyridinium chlorochromate. Now that is the reaction. If you want the mechanism, you may write the mechanism of the reaction. Now then another oxidation reaction, that is dehydrogenation reaction, that is removal of hydrogen from the alcohol using copper powder heated at 300 degrees Celsius. Now when a primary alcohol is passed over heated copper at 300 degrees Celsius, dehydrogenation occurs from the CH2OH group, one H from here, one H from OH, so CH double bond O is created plus H2, and aldehyde is the product. Now secondary alcohols are dehydrogenated to ketones. We take this compound isopropyl alcohol. Two H atoms are removed. We get C double bond over here, and we get a ketone, that is propanone or acetone. This is isopropyl alcohol or 2-propanol or propan-2-ol. Now, tertiary alcohol is not dehydrogenated, but it is dehydrated by copper at 300 degrees Celsius. You take tertiary butyl alcohol. One of the atoms of a methyl group combines with OH, producing a double bond here. We get this compound. It is 2-methyl 1-propane. Now that is the dehydration product. So much about action of copper powder and various branches of alcohols. By this method, we can differentiate between primary, secondary and tertiary alcohols. Now, primary alcohol gives aldehyde. Now, aldehydes can give a bright silver mirror with the tolerance reagent. You write all these reactions. Now, tolerance reagent is a solution of silver hydroxide in ammonia, a clear solution. Aldehyde is a reducing agent. It will reduce the silver ions in the medium to metallic silver, and the silver will be deposited on the inner side of the test tube in which the reaction is conducted, and then the test tube will act as a mirror, because a mirror is formed when there is a coating of mercuric oxide or silver on one side of the glass plate. So we call it silver mirror test. So aldehyde can give a silver mirror test because aldehydes are reducing agents. A ketone cannot give silver mirror test, but it will give a derivative with 2,4-dinitrophenylhydrazine, abbreviated as 2,4-D. So this is a reagent which can give an orange precipitate with a ketone. So aldehydes can reduce tolerance reagent to metallic silver, Ag is deposited with 2,4-D, 2,4-dinitrophenylhydrazine. A ketone gives an orange precipitate. Now an alkene can be treated with bromine water. A bromine water is having a reddish brown color. When bromine is removed, we get a colorless liquid, that is water. So decolorization of bromine water, removal of color from bromine water, is a test for unsaturation. So this alkene will decolorize bromine water. So a primary alcohol, a secondary alcohol and a tertiary alcohol can be differentiated using this reagent system, copper at 300 degrees Celsius. So that completes the reactions of alcohol. That is enough. Thank you.